feel free to use any of the CSV files that you'd like. What is combined? I don't remember now. We combined two spreadsheets into one, but I don't remember which two spreadsheets it was. But you can take a look at it. It could be Titanic. It could be. I think it may actually be Walmart. I think there was a training set and a test set, and I think the combined might be both. I'm not positive, but you could pull it up and you can look at the columns in it, and you could probably figure out what it is. And if you do the credit card use case, we'll give you a little bit of a little information about the data set. So you're trying to predict whether they're going to default next month on their payment. Some of the information that you're going to have in this data set is the age of the credit card holder, their education levels, the historical payment status, what they've paid over the last month, whether they paid a month ago, 2 months ago, 3 months ago, 4 months ago. That's the pay 0 through pay 6. The historical payment amount, so the amount that they paid, their bill amount, what they were billed, and you're predicting whether they're going to default next month or not. So you can run this, and it's fairly easy to determine. When you see the results, it's going to be fairly obvious. But there are some neat things in there, and you can group them and see. Does sex have any impact on whether they default or not? Does age have any impact? Things like that. So it's a very simplified use case, but it fits very well in a 1-hour lab format. The Walmart one is more interesting, but it runs for a little bit longer. So that's it. Go ahead and go through the labs, and if you have questions, you can ask Neil or Glenn or myself. Hospital readmissions is an interesting one. So it has to do with a diabetic use case. They said people who are diabetics get readmitted into a hospital more frequently than people who are not diabetic, like 3x more likely to be readmitted.
Type 1 or type 2?
I don't remember. I'd have to look at the data set to find out. I think there's an airline, the airline one, the airline customer sat one might be out there somewhere. I don't know if it's called customer sat or if it's airline customer sat. But I want to talk about some of the things that are going on as we go through the lab. So what we did here, we had some folks from IBM Research that were nice enough to help us out. They did a workshop session in Seattle, and the way the workshop worked, you went in and you brought your own laptop, and they would they developed a course and took us through writing a TensorFlow program. And so I'd like to give thanks to the guys from research who did this. The challenge that they had is folks from IBM Research are folks maybe not unlike the folks in this room. They don't go out and speak to customers. They don't go out and speak to anyone. They sit in the basement and write code all night. And so I ran into one of the research guys that was going to be doing the session at the hotel I was staying at. And I said, oh, I'm going to the same event. I'm going to your session. And when I was talking to him, he was looking down at the floor, and he wouldn't make eye contact with me. And he talked about how, he's never presented before. He was really, really nervous, very, very uncomfortable. But his boss was forcing him to leave the basement and go out there and interact with other humans. But the challenge they had is they took what they had, and their lab was, okay, we're going to give you a piece of code. Now please type that into your Python file, and then we'll run that Python file and get some output. And it wasn't quite like this, but I was sitting in the back of the room, and I was trying to type the program, and I failed miserably because I couldn't tell the difference between colons and semicolons and single quotes and double quotes, complete failure. So what I did was I took what the research guys had built, and I put it all in Jupyter Notebooks, kind of no-brainer. And so now we've taken what was a 4-hour lab session of me trying to type their program, put it all into a notebook, and you can click through it. But what we'll do is talk about what we added at each phase as they took us through that workshop and they had us typing everything, okay? But we can talk about what we added as opposed to talking about what to type. Make sense? All right. So still using your team numbers. You do have a hard copy of the lab guide. There's also a soft copy out in Box in that same directory we had earlier. You can download the IP addresses that you'll use. It's probably the same IP addresses, but it's a different port number now. We have the containers running using a separate port for TensorFlow and same containers. But what we're going to do is when you get into the Jupyter environment, you can log into the Jupyter environment with ABCD1234, the same password that we had for the laptops. And there's several IPYNB files out there. There's a code 00, code 01, code 02, all the way down through code 16. These were the 17 iterations that we went through in the original workshop of, write 7 lines of code and execute it. Now add an additional 10 lines of code and execute it. And so this is each phase of that process. I combined all of those notebooks into a single notebook, code 00-16.ipynb. And so now you can just execute the first code snippet. The second code snippet will be the same as the first with an additional, few lines of code. And so when you get to the last code snippet, code 16, it'll be the full 150-line, program. Does that make sense? So you don't have to execute them progressively because each code snippet kind of stands on its own. But that's the idea. We'll go through the notebooks together. You know how to use Jupyter. We can just run each section. So we'll start with code 00. This was the first typing test that I had back in Seattle. But we're just creating a framework here. We're creating a one-hot vector. We are using, I should have backed up, we're using the MNIST data set that we talked about yesterday. 60,000 training images, 10,000 test images, the black and white images, white background, black text, 28 pixel by 28 pixel. And we're going to try and predict, based on that test set, what a number is. It's the characters 0 through 9. so 10 elements there. So we're creating a vector of 10 elements. It'll be mostly zeros. There'll be a 1 in a place, and it's the zeros place, ones place, twos place, threes place. So this would be representing the number 3. It is a labeled data set, so we'll read in both the image and the known good label. We'll store that, we'll train against it, and then we'll test against that known good label in the end. So here we've just defined, a vector. That's it. So you can execute this line of code. It's going to download the MNIST data set and extract it, and then it's going to do that every time from here on out. Then we can run, I forget the parameter. There's like a reset function. What's it? I don't have it. Yeah, so that'll reset the environment. We had some problems when we combined the notebook because one notebook would leave some things open. And so in between each code snippet, we're doing a reset to say, wipe everything out. So you can execute that. And then we'll get to code 01. So code 01, we're defining, a two-dimensional. It is a two-dimensional image. We're going to read that. We're going to flatten it into a one-dimensional image, 784 elements, 28 times 28, 784 elements. And so we're going to read this image into this array. And then we're going to store the known good label in a placeholder here called y underscore. So somewhere in this program, we're going to make a prediction. The prediction will store in y. The known good label will be stored in y underscore, and we'll compare those two to see how accurate our model is in the end. So you can go ahead and execute code 01. What's that? Yeah, so you can execute, yep.
So when we execute, let's say, code 03,
yep.
It's kind of already doing twice of the code 00.
It is. And so it's progressive where we've just added additional code in each section. So we're rerunning the same code multiple times. And that's why we had to do the reset, is because some of the things you can't open multiple writers. If we leave files open, it creates problems. Does that make sense? And the problem was we weren't always adding at the bottom. Sometimes we're adding at the top, and so that's why we did it that way. I don't know if it's the best way. So that's code 01. And we'll take a look at code 02. So we're going to define a weight and a bias, two variables that we're going to tweak during our training. So we're going to initialize those with a small value there of 0.1 initially. How do you decide what kind of weight to initialize your variables with? You could use any. Why do we initialize the weights? Why not just leave it?
Well,
You've got to start somewhere. Why not start from 0, I guess? Zero does get stuck, and it could, I think a small positive value helps break symmetry in the models. And so we're starting with 0.1. You could probably pick a different value there, but a small positive value is a good place to start for the weight. And it will be modified as we train the model.
So it looks like it's generating a random number with the same computation.
Yeah, correct. So we initialize the weight and the bias, avoiding dead neurons. So you can run code 02. And we'll take a look at code 03. Here we're going to use a simple, softmax regression model. So we're just simply going to multiply, the weight, add a bias to produce our prediction. So, why softmax? So softmax, it's not required, but it's good when we're trying to predict our probabilities. So it assigns our probabilities at the end. All the probabilities in the end will add up to 1 or 100%. So you don't necessarily have to have this, but as you're producing the results, it's nice to have something that adds up to 1. It's easier to look at and understand. If we take a look at code 04, we're going to calculate our accuracy here. So we defined our accuracy using an average of correct cases, and we're going to compare our prediction y to our known good label that we had of y underscore, and assign that to our accuracy value. And why are we using argmax here? That's exactly right. So yeah, it's an extremely useful function because it gives you the highest entry to say that this is my prediction. So you can run code 04. Got a handout? Another hand? Oh, there's a handout. Okay. So you can run code 04. Code 05, we're going to create a session here. You know, we'd like to have an interactive session showing us some of the steps in our training output. So we'll define SES, S-E-S-S, as our interactive session. So you can run that. And actually, I think that one actually produces an error. And that's okay. No, it's because we didn't initialize our variables. So this is, you know, a rookie mistake. Code 06, we're going to initialize the variables, tf.global underscore variables, and initialize a run. So code 05, we intentionally baked in an error. But you can run code 06. Correct. The variables we defined in code 05.
And those are going to be what? The TF placeholder, whatever TF placeholder is.
Yes. So then we'll take a look at code 07. So here we're going to increase our batch size. Initially, our batch size was 1. We're going to move that to 100. We're also going to add some logging. So every 100th iteration of our training, we're going to print some output to say where we are in terms of accuracy. So why do we change the batch size? How's batch size important? Yeah.
So it should basically improve your accuracy or the training.
It can, but it also has to do more with throughput. Rather than running one image at a time through the process. Remember, these GPUs have 16 gig of memory. The newer ones have 32 gig of memory. And so if we can fit many images onto the GPU at a time, we can train more quickly and iterate more quickly through the batches. Now, remember, as we go through and we're going to define some convolutional neural nets, while it's a 28 pixel by 28 pixel image, we're going to have more copies of this as we build our CNNs. And so we'll have 32 copies of the image initially, and then eventually 64 copies of each image as we produce convolutions of that image. And so, picking your batch size here is kind of an art form because you need to decide how many copies, how many layers I'm going to have, how many copies of each image am I going to have, and will it nicely fit into my memory footprint that I have on my GPUs. Does that make sense? So in our case, it's 16 gig. It'll easily fit because they're very, very small images in this case. And we could probably even use a larger batch size. But in your environments, understanding the data set, understanding the images that you're writing in will help determine the batch size that you're going to select. So you can go ahead and execute code 07, increasing the batch size to 100. So at this point, if we tried to view graphically what our models have learned thus far, we're going to have negative and positive weights. If we represented the negative weights here in red and the positive weights here in blue, if you were to try and look at these images, and I know some of you do a better job of this than others, could you accurately predict what numbers each one of these images were? Yeah, some of you guys are smarter than the average computer. 0 and 1 are easy. Even I can see that. 3 and 2. 2 is pretty good. Oh my gosh, I need better glasses. Yeah, they have something I don't. I don't know. The 2 is good. Okay, yeah. Okay. 6 is okay. Man, you guys are. You like 3? Okay.
Yeah, 5 is 5. I can kind of get, but if I was looking at it, I wouldn't pick it up.
You're seeing things I just don't see. That's okay though. We're going to try and clean it up a little bit so that maybe the rest of us can see what you're seeing. And so eventually we're going to go through this and we're going to do rectified linear units, ReLU, and we're going to remove some of the negative values from this. And we'll talk about why we do that in a moment. But at this point, I guess you guys can still see what it looks like. We could enable TFDBG for a TensorFlow debugger. This could give us the option to set breakpoints, inspect variables as we step through a program. We don't necessarily need to do that in this section because we've put everything in a notebook for you, so you're not writing it yourself. But it could be enabled there. You could do a session and set tfdbg.local CLI debug wrapper around your session. It is not in here, so it's not a code 07. The other thing we're going to do, I know about half of you were using TensorFlow yesterday. Is anybody using TensorBoard at all? Some of your users? What do you use TensorBoard? What do your users use TensorBoard for? They like GUIs. That's a good enough reason for me.
Fundamentally, that's what it comes down to.
If it doesn't come in a GUI, they're not interested.
Yeah, if it's a command line.
Command line, forget it. We know guys like that. And we know other guys that have never seen a GUI that they like. We're going to add some stuff to the program to log some information so that TensorBoard, we can actually launch TensorBoard at the end and see the visualizations. Unfortunately, there's a lot of stuff, actually almost the rest of the stuff that we're adding is almost all specific to TensorBoard. So we're just going to cut and paste or add a bunch of this stuff in there. So it does give us a GUI to visualize some of the information. We'll take a look at it when we get to the end of the lab. But code 08 is going to set a log directory. It's within your container. The log directory is TensorFlow_logs /mnist _deep. And it's going to store a bunch of output files there that TensorBoard is going to use to produce the amazing GUI that some of us enjoy so much. So code 08 just adds a line there to say where my log directory is. It's not actually logging yet. Code 09, it's not there yet. And then code 09, we're going to try and give some more meaningful names to some of the variables we've defined, so that when we get into TensorBoard and look in the GUI, as we mouse over things, they'll have names that mean something to us. So we've set names for, our weight, our bias, the labels, things like that. The better the name scopes here, the better your visualizations will be in the end. So you can run code 09. Code 10 is going to allow us to actually see some of our actual images that we've used within TensorBoard. So we'll see that at the end. So we've added some sections there to run, to use the actual images that we've trained against and we'll be testing against. And then code 11, there's a tab within TensorBoard for histograms and scalars. We're adding some code there so that we can populate that tab with some graphs. And so we'll get to the TensorBoard GUI at the very end, but we had to add all these code snippets so that TensorBoard would function. So at this point, what can we do to improve our model? So we're using softmax regression. And do we see the accuracy results now coming up? What's your accuracy on your code 11 run? The training. 0.96 in the test? 0.9? 91. 91% against the test. Does anybody have anything better than 91? 91.88, okay. What's that? 919. Oh, that may be the highest number. Nobody at 92. Nobody at 92% accuracy. At one point, yeah, if you rerun it, it'll change every. Why does it change every time? Why isn't everybody getting the same number? It's a batch. It's non-deterministic. And so our batch, we're randomly selecting images here that we're running against. It's not the same. While it's the same containers, they're all identical. We are selecting different images to look at every time. And so if you run it, multiple times, but they all kind of converge at the same number. So softmax regression is going to peak out around 92% accuracy. That's really all we can get out of that. So some things that we could do maybe to improve accuracy. You can tweak the algorithm parameters. Maybe you can train longer, but training longer doesn't always increase accuracy. It only increases accuracy to a point. Eventually it goes down. You can get more data. You could build a bigger model, more layers within your model. So a couple different things we can do here to maybe increase our accuracy. So some guidelines for this. Andrew Ng, professor out of Stanford, produced some gap charts here. And so we have, I don't think we showed this yesterday. My days are running together because we did this on Tuesday. We have an optimum level of accuracy up there at the top, kind of a darker blue bar at 99% accuracy, kind of a limit approaching 100% accuracy. Our human level accuracy is generally accepted to be 98% accurate. Now, obviously, there's smarter humans and
Is that on a particular data set?
this is just in general. This isn't. I think in general in machine learning, they're saying once you're at a 2% error rate, that's a human level accuracy. I don't know if it's just vision problems. That's a good question. It could be just vision problems. Yeah, that is true. That is true. Maybe it is vision related. I'll have to go back and look and see where we took this out of. Maybe it is vision related accuracy. And then the bottom three bars, the training, dev, and test. These could actually be in any order, but gaps between our optimum accuracy and the bottom three bars could tell us techniques to try. So if we had some guidelines here, if we had a large gap between our human level accuracy and our training accuracy, maybe we have a high bias here. Glenn showed some charts yesterday with some bias that we're going to fix, right, Glenn? It's funny how it just pops up and you go, wow, that does look a little biased. But we could, maybe build a bigger model, more layers within our model. We could potentially train longer. We could iterate until training accuracy is high. If we had a large gap between our training accuracy and our development accuracy, maybe there's a high variance in our data set. Maybe we need more data again. Maybe we have some images in our test set that just didn't exist in our training set. So maybe we need to go back and look at what we have within our data sets. Maybe you just need to iterate longer until your development level accuracy is higher. The other thing we're going to do is we're going to build, a CNN here. So we'll build a neural net. We are going to use rectified linear units, ReLU. And what this does is it drops all of our negative weights that we talked about earlier when we showed the pictures that some people could see really well with the blue and the red pixels. We're going to drop all of the negative weights, assume that those are 0, and it's going to increase our performance, but we don't really sacrifice anything in terms of accuracy. So it's kind of a plus with no, a pro without a con, if you will. So we're going to use ReLU as we go through this. We're also going to add a fully connected layer at the end of our model. So we'll have our input image here on the left. We're going to do a convolutional layer, a ReLU layer, a pooling layer, a second convolutional layer, a second ReLU, a second pooling layer, and we're going to end with a fully connected layer. I did ask, when I was in Seattle, I asked one of our research guys, I said, why is the fully connected layer always at the end? Why can't you put the fully connected layer, why can't you have multiple fully connected layers? Why can't you put the fully connected layer in the middle somewhere? And he sat and he thought for a little bit, and he said, I don't think I'm qualified to answer the question. And he said, basically, he's doing it because that's what everybody does. We'll leave it. Anybody have any comments to that? Why we end with fully connected layers? To populate the prediction buckets. I think everything has to be connected to everything so that any prediction could go into any bucket.
And my guess is they wouldn't put one earlier just because it's expensive. That's what I was going to say.
Okay.
That would be my guess.
That sounds like a better answer than the research.
Fully connected networks, you have a chance of overfitting.
Okay. So you don't want to have fully connected layers everywhere.
Yeah. So you want to test with others, and then you also want to verify with fully connected.
Okay.
Theoretically, you could get the best accuracy, but you want to know why you're getting it.
Okay.
Fully connected once and then never do anything else and done. You could just end up with a overfitted one.
Okay. That sounds like a better answer. Okay, we will add a fully connected layer at the end. Go ahead. No, please. You don't want to share? Okay. Okay, that's fine. Other things we're going to do, some other techniques, we're going to add a dropout layer. Now, when we ran this on Tuesday, somebody said, well, it used to be common practice to do a dropout of 50% to avoid overfitting. And he said now, the gentleman in our class on Tuesday said, that's not true these days. He said dropout now is, commonplace is 20%. What say you? 20%? I'm getting some nods. I'm getting some shrugs. Any opinions there? You don't care?
I don't.
Oh, I shouldn't say that. Okay. That's fair. So I'll challenge you, because I didn't check with the guy on Tuesday. I told him, I said, your notebook's going to drop out at 50%. Change it and drop out at 20% and see, does it change anything? And I didn't circle back to him to find out. So if you want to try it, try dropping out at a different rate. We will stop early. Why don't we train longer? This was. Sometimes I think I'm a simpleton. In my simple brain, it was somebody who's training for sports. More training is always better. They can just continue to train, get better and better and better, right? How can you overtrain? And when you think about it, if they were training 24 hours a day, eventually their performance is actually going to decrease. So it actually does fit. It is an analogy that fits.
There's probably still some saturation level if they keep training.
Yep.
Like maybe they're not going to get worse, but they're not going to get any better.
No improvement.
Sacrificing
It's time with their family, or sleep, or muscle recovery. They're more like So it does actually fit, but also within models here, what you'll see is all the curves continue to increase, but they'll all peak at some point, and if you train beyond that point, the accuracy actually goes down. And so we do want to stop early as opposed to stopping, beyond that peak. And so we will do that. Weight regularization, we talked about that earlier. Large weights, indicate that we've overfit. And so we did start with a small weight earlier. And there's many, many other techniques, but we're going to use a couple of these as we go through the model. We're going to build our first CNN here. So code 12 will define our first convolutional layer. So conv1, we have that 28 pixel by 28 pixel image. We're going to have 32 features for that image. Now we're going to have 32 copies of that 28 pixel by 28 pixel image. The size of our kernel, size of our filter will be a 5 pixel by 5 pixel filter. And what you'll see in a moment, we'll have a stride of 2. And we'll implement a pooling layer. So we'll define pool 1 there as well with code 12. So at this point, once we've added all of these, I don't know how many lines of code we've added. With code 12, we have our first CNN, our first ReLU, and our first pooling layer all defined. So we have our input image here at the left, 28 pixel by 28 pixel. We have 32 features, 32 filters, and then we're going to pool that down to a quarter of the size, from 28 pixel to 14 pixel by 14 pixel. Okay, so it's half the size. Well, it's a quarter of the size, right?
Oh, well, I mean 14.
Yeah, but 14 is half of 28. So, it's similar to what we did with the softmax regression earlier. Only the weight here has been rewired to better fit the tensor shape. So that's code 12. What's our accuracy at now with code 12? 9635. 96? What's that? 9192 with code 12? Wait a second.
There. Test accuracy, training accuracy is 0.86. Drop down. It keeps dropping down from 900 to 1,000.
Run that one again. That doesn't look right to me. And you might have to, you know what? Do this one first. Because I think it's going to give you an error if we don't. $97. I don't know how you got 90. That's odd. So we've got almost a 5% jump in accuracy here, just using a single CNN, right? So we went from around 92% to somewhere around 97%. Yes. What did she just went back and ran it a second time and it worked. So if we go back up.
So first time it's just.
I don't know. Maybe you skipped. Run this one. I believe you. 97. I don't know. I don't know why. Two of you got 91%. So we've implemented a single CNN here. Code 13 is going to add a second convolutional layer to our model. And so we had a conv1, pool1, and now we're going to define a conv2 and pool2. And when we take the the 64 copies of the 14 pixel by 14 pixel images, we're going to pool that down to 64 copies of the 7 pixel by 7 pixel images. So after 2 rounds of downsampling, our 28 pixel by 28 pixel image has been downsized to 64 feature maps, each 7 pixel by 7 pixel. And when we get to TensorBoard, we'll be able to actually see these features.
And again, I dropped accuracy.
And you dropped accuracy. Again?
Yeah.
To what?
So now I'm at 94.
94? What's everybody else at?
Like
94, 95. So adding a second layer here did not help. But we're gonna add a fully connected layer here at the end and see what happens. So more layers isn't always
Right, just like more cores is not always good.
exactly.
You can get speed down.
Exactly. 94. So we're at 92 up to 97. Now we're at 94, 95. So we've gone up and back down. So more layers doesn't always mean more accuracy. We will go ahead with code 14, add a fully connected layer here at the end. So we'll define FC1, our fully connected 1, and use our 64 feature maps, 7 pixel by 7 pixel in size. And what's our accuracy now with the fully connected at the end? 97 and change. Yeah, okay. Is anybody beyond 97 or far below 97? Everybody's around 97. Okay. That's fair. So we are going to add the dropout layer. You know, for dropout probability, we do a dropout to help prevent overfitting. It's a way to regularize our layers. Is it the keep prob? I think keep prob is it. That's a good question. Oh, keep prob. It's up there in yellow. It's really easy. It's on the screen here. Keep prob's up top. And then it's further down as we're doing keep prob of 0.5. Okay, we're almost there. We're going to worry about the embedded visualizer. So code 16, the final piece of code. This was kind of the final sprint at the end of the session in Seattle, where they gave us several code snippets to add at various points in the program so that we can see the embeddings within TensorBoard. So code 16 has you add several pieces here for the embeddings. And this is, it creates some of the thumbnails that we're going to use within TensorBoard. And we're going to visualize against our test data. You can run code 16. So think about this, deep learning projects are highly dimensional. 784 pixels here into our input vector, but this translates into 784 dimensions. Bigger projects, you're going to have dimensions in the millions, tens of millions, hundreds of millions. And when we try and visualize highly dimensional data, there's challenges there because we're trying to represent, yes? Yes.
So in one of the sessions, I think your colleague presented,
Yes.
Those images can have arbitrary size. I'm just trying to understand, when you try to pull in a standard model,
Yeah.
how are you kind of taking care of, the image sizes across that?
That's a great, I don't know, that's a great question for Neil. He wasn't listening to you, though. He's doing his email back there. That's okay. The question is, we've standardized here. We've got 28 pixel by 28 pixel images. We're reading them into 784 element vectors. When you do stuff in Vision, and you have shapes that are not rectangles, you've got polygons, how does it take and build a model from, these oddly shaped dimensions? Is that your question?
Yep.
Okay.
So the answer, pulling it up now, I've got it. This gets asked frequently. We do pre-process the images down, and the answer is for image classification, they scale them to 224 by 224.
Okay.
And for object detection, high res, they scale them to 1,000 by 600.
So the short answer is, it doesn't matter what you draw around a box, it's going to make it fit into the box that it wants. Pre-process it to make it fit in the box.
Release, like I said before.
Okay.
Distributed deep learning and high res and all those things, they're features that are coming. They're not there today.
Okay.
So maybe add with a zero values on those outside of non.
Yeah, you could. Okay, so what was our inaccuracy? It was 97%, I think. Is that 97 something? Okay. So we do have, I don't know how many lines of code it is in the end that I had to type that you guys just had to click on. We took that 150 something line program and we tried to create an equivalent program in Keras. And I know yesterday I think I asked, anybody using Keras instead of TensorFlow? Many users do because it's a lot easier to do. So what we did is we took the same program, we tried to execute the same things, and again, Keras is kind of a wrapper, and it's using TensorFlow under the covers, but we produced the same program. So if you do a file, close, and halt, inside that same directory, I think there's something that labeled like Keras-model maybe, or Keras something. If you open that and execute that program, that code snippet, it's, I don't know what it is, 20 lines of code as opposed to 150 lines of code. It does use a different optimizer. We're using the Atom optimizer instead of, I think we use gradient descent in the TensorFlow model that we built. What kind of accuracy do we get from the Keras? It's going to take a little while to run. 98%. And you're at 15% of the code. And so, to me, this is a reason that a lot of people say Keras is a lot easier to use than TensorFlow. It doesn't have all of the things that you can do within TensorFlow natively, but when you talk about like Kaggle competitions and trying to start quickly and build your model and see what's going to work, try different optimizers, try different algorithms, you get an idea with Keras, and then maybe to get the last 0.5% or percent increase, maybe you go to TensorFlow to do something that's TensorFlow specific. Yes?
Your Keras, your dropout rate is 20%, I guess. So some of the parameters is kind of different.
There are some different, it's not identical. It's not an apples to apples. But it is using the MNIST data set, but it's not an identical, yeah, it's not identical. I should have made them identical, but that, oh well. Next week, we'll have it all new jokes, all new materials. Okay, with that, any questions about the TensorFlow Keras, please? We're going to go into TensorBoard next. So I don't have a screenshot of it, but it is on the handout. It's on the very back, I think.
Yeah, it's almost the last page. The one we just
Oh, and actually on the very back, it has the IP address and the port number to use.
the page just inside.
And and the page just side. Okay, same thing. Man, I put it in there twice.
How to figure out the hashes. Yeah, but you could.
Yes.
Just that you're basically introducing four models, what is the right way to really kind of visualize what you're trying to construct? For example, the first argument is flat, and the second one is the dense, and then the dropout, and the dense. How are you actually able to connect those individual components as a bigger model?
I'm not ashamed to say I don't know. Is that a fair answer? But what I did is I found this, and it was similar enough that I said, let's compare the two. What I'd like to do is go back and have an explanation as to what they did to write this, and I don't have that today. Because it's not identical. It is using the same data set. And it is using, but I don't know what a dense layer is versus a CNN. If that's what I don't know the answer. Good question though. And we actually had the same comment on Tuesday. They said, I'd like to know more about how you did this. And I said, yeah, that would be good. I'd like to see that too. We'll get there.
So, like for example, I think this particular function call is for the two layers here. Like for example, if I want to put like five well layers.
Yep.
One after another. So of course I need to make some changes, and just try to understand how you basically can construct the whole.
Yeah. No, I get it. It makes sense. I just don't have that in here today. All right, so if you fire up TensorBoard, we'll kind of wrap this lab up. I don't have, well, let me see. Do I have a, Glenn, you didn't do the lab? No? Yeah. Team 11 did? Okay, so Team 11 is System 3, so that's 10, 31, 204, 155, 6011. Okay, so you can scroll through these. We can see that the scalars tab that it launches initially. We can see our accuracy graph. We can see a loss graph. What's that? Why is this? I don't know the answer to that. You think there's a problem with TensorBoard, or you think it's a problem with our program? Yeah, that does look like there's an issue there, right? And I don't know what these light lines are either. They're definitely going to 0, 0? Oh, these are. Okay. Let's go back and look. I don't know if that was always there. Has it? Okay. I'll look and see. I don't know the answer to that. And do we see the same thing on the, yeah, we see the same thing down here as well for the loss. What if we change the smoothing? No. That's a good question.
I found the projectile change pretty cool.
Yeah, the project, yeah.
That's what, yeah, that's the grand finale. That's the grand finale. That's okay. It's good that you guys are already there. You can take a look at the images as we go through the convolutions. Remember, we went from 28 pixel to 28 pixel to 14 by 14. Yeah. Resource exhausted. You want to take a look? I bet there's probably still something. Maybe you can stop the notebook. You can look at the convolutions, the outputs there, so we can see the outputs there. I'm going to challenge some people here, Lauren. You can see things in everything. You've seen everything. Every picture we put up here, you've seen something.
Yeah, I looked at these.
You couldn't see anything? Now they don't make sense to you. Okay. That's good, because I was starting to worry about you a little bit. But you can look at the 14 pixel by 14 pixel images. You can go down further, and you'll see after the second convolution, you can see the 7 pixel by 7 pixel images. The machines can see stuff here. It's not human readable at this point. So you can look at the images there. You can look at the graphs. You can kind of get a visual representation of the model that we built within TensorFlow. You can click on objects and see, our weight, our bias. Oh, these are the data powers. We can see our weights, our biases. within here. To the optimized layer? And what's the size of these lines? That's a good question. I don't know the answer to that. We had some theories last time. If you zoom in, I think there's some text on some of those. See if I can. 12 tensors there, 9 tensors there. But we've got 9 tensors here, 9 tensors here. So it's not just strictly the number of tensors. I don't know the answer to that. Somebody asked me that the other day, and I don't know the answer of the size of those lines. We have to find somebody who's more well-versed in TensorBoard, maybe. We can look at the distributions here. We have some other graphs to look at. You can look at the histograms, and we can see our histogram plots. And then the grand finale that some of you have already beat us to, you can take a look at the projector tab. You can change the color map there to give each label a unique color. And you can probably look at this late at night and just think, wow, this is great. The other thing we can do, we are using principal component analysis, PCA here. You could switch to T-distributed stochastic neighbor embedding, so T-sign. And it'll continue to iterate down here, and it'll say, who do I look the most like? I'll take one image and say, who is my nearest neighbor? Who am I most like? And what you'll start to see is that there'll be, it's hard to see here, but you'll see some numbers mixed in with, we've got a grouping of zeros there, and maybe there's a 6 in the middle of the zeros because it looks a lot like a zero, just has a little tail at the top. And so this might be a way, I don't know if people are using this normally, but to find outliers or find images that are causing me heartache. Maybe this is one that, maybe I was only 60% confident that was a 0 or a 6. And maybe this is something, and what do you do with those? What do you do with outliers in your data sets? The answer is it depends. If it's a true outlier, maybe you get rid of it. But sometimes there's interesting things that happen in outliers, and so maybe we need to explore, why is this an outlier? Do I need to get more images that look like that to train better so that I can better understand, why I wasn't 99% confident that was a certain number? So it's a way to group them together. Look at your data sets. Now we're only looking at 1,024 of the points. Remember, our test data set had 10,000 points, so this is a small subset of the bigger data set. But you get an idea of what you can do here. Are there questions or comments? Is lunch here? All right. Yeah, let's do that. Any questions before because your containers will be gone eventually. We'll leave your containers through lunch and we'll kill them at the very end. Oh, what? Neil's decided he's going to bounce the box. Okay, 12:30. Compromise. Any other questions? Your projector fails? I had that the other day.
Maybe I did too much.
No, I got the same. It could be that you did too much. You have that problem often? No. I had the same problem, so I don't know. You can go. Yeah. Try going to. I had the same problem.
I tried closing everything.
I tried rerunning it the other day.
I have a terminal going. I'm running top. I don't know what this is.
I don't know what that is either.
Yeah, that seems to be. Well, TensorBoard is using 10 gigs.
Mm-hmm. Mm-hmm.
H-top is not on here.
You could use the one I'm on if you want to see it.
I can see
No, I mean,
That's fine.
you're welcome to it, though. Yes. Glenn, any idea what,
Oh, this, when I,
you showing me a process there?
oh, yeah, this process, the ZMQBG.
What's that?
You're seeing the weight, so you should be.
You never got the column to predict?
Yeah.
A bunch of different columns that
I have to go back and look at it again, because I know we put it in there. I don't remember if it had a good column. It was readmission was the column you're predicting, right?
Yeah.
Okay. I'll go back and look at it.
There
I
was
don't.
another one that was similar that had high, like.
That's the problem. We got all these guys dropping things in there. None of the people looking to see, is this something good that we should leave here? Yeah. Yeah. Now, where do you do the online courses for BU or MIT? Okay. Very cool. Is it part of what program is it part of? Is it part of MIT proper, or is it like edX or?
Obviously, those aren't the real PIN numbers then. So those are kind of some kind of translate.
Yep.
If you
Okay.
actually open up a putty session and log in, which you can.
Yeah.
You can upload a putty session to this.
Well, this is in a container, right?
Okay.
Yeah, it's in a container,
But
but
if I open up the putty, that would go into a container too, right?
no, actually, we get into the host.
Oh, okay.
Okay.
So you could log in with
That's really cool.
31, 204, 51.
How cool! Wow. And who takes the courses? Is it? Yeah. So can I send you a note? And get, I mean, I would love to. Okay. Better be taking notes here. Oh, I'm sorry. I'm not gonna. No, it's fine. You're fine. You're fine. I'll just watch.
Yeah, okay.
So, I mean, you see, if you ran top of there, it'd be
Yeah, just say it. Yeah, except
very different.
we know.
Okay. So this is on the bare metal.
Yeah, you're actually logged into the host OS.
So this is edX, just to give you a sense of how the course works. This is the Builder Radar. We have an advanced database technologies course, which is why we're saying it's about the data, we're looking for data, and we're building out the practical machine learning.
Oh, wow.
And so the basic to the practical machine learning is, this is, for those of you who don't have
Which is
like
probably
your own,
nice to do on a shared.
Yeah, AC 922 or whatever.
These are, this is running them on a supercomputer. So pretty much we've got the bare metal, you're running it through Scheduler.
Yeah.
We're going to give you some background, and we also use the MNIST data set. I just got our Jupyter notebooks released.
Very cool.
And so there's some other stuff in there. So just got those publicly released from the lab. Just got the email this morning. So we'll be using those to build out this course. Plus, we have this tendency.
And it did have a higher.
Our strength is that the way that we're doing this.
No, you're good.
The way that we build these, or our thinking is
You're good. You're good.
it's been a systems test, right? So systems engineering is sort of where it's at. And so you need to think of a supercomputer, not as just, I'm just going to take this and run it. It's a different system. Think about the entire system. So, so we're starting with this, we're redoing our HPC course, which will be out there. But the same thing, we're taking the same idea here. There's that pipeline. I mean, I think someone had the chart yesterday where they had all of the people.
That was Glenn.
And the
Yeah.
ecosystem. And we tend to think of it, that whole systems thinking, that end-to-end is a systems view of the world. And so you're somewhere in there. And what's happening somewhere else is going to affect. But you do what you do is going to affect somewhere else. So you have to think of it as the whole system. And sort of one of those balance boards, someone moves some way on one of those balance boards, and other people are going to end up somewhere else, right? And so I've got to get like a simulation, probably not allowed to do that. Because it's not just a balanced beam, it's a board, it's a big space. It's a multi-dimensional space, and so you have to think about where you are. But basically, one of the things that we'll go through is understanding the trade-offs. So all these buzzwords, so you can do big, huge cloud. I've been thinking about this. I hadn't mentioned. Do a giant word cloud. No, buzzwords and important words. And start slowly pulling them into like different, like these are the glossaries. So we start.
You can have a graph that looks like this, and it just my nearest neighbor.
Yeah,
That would be good, because then you'd be like, oh, that's just this. That's just a rebranding of this thing. It's been around for 100 years.
Right.
Yeah.
100 years.
PCA.
200 years.
It's just eigenvalues.
Even PCA itself has been around.
Right,
Yeah.
but it comes from eigenvalues
Yeah.
because we couldn't
What
use
is
the
an
term.
eigenvalue?
We couldn't use eigen during World War II.
Because they were like, oh,
It's German. because I think it originally came from the idea that when you're looking at, again, mechanical engineering stress and strain, those are the principal directions of stress along the principal
the other
axes.
is